Today we're going to start rotational motion, and I'll let you pause so that you can read this cartoon. It's one of my favorites. And so far, we have done all of this stuff. We did translation, we did kinematics, so translational motion with kinematics. We've also done dynamics and net force, so those free body diagrams and some of the forces equals ma. We did energy, so mechanical energy and work, with everything but a lot of the gravitational energy. We haven't done everything with gravitational forces yet, but we've done spring forces, tension, friction, drag, all that kind of good stuff. And we've also done linear momentum. So we've covered, 2/3 of everything that you're seeing on your screen. What's really cool about our rotation unit is that we get to redo everything and review everything, except that now it's going to be rotating instead of translating, and everything is analogous. So you have rotational kinematics equations that are very similar to the kinematics equations. They're just Greek. We have net torque is equal to I alpha, which is very similar to net force is equal to ma. We've got angular momentum that is conserved. We've got rotational dynamics, where we can calculate things that are rolling down a hill and stuff. So it reviews everything we did last semester and then makes it rotate. And it's my favorite unit of the year. I love doing rotational motion. It's also one of the harder units that we do. So we do it now, early in the semester, and then the two easier units that we'll do after this are both very short, and then we can kind of ease into reviewing for the AP exam after that. All right, so angular displacement is theta. So sometimes delta theta, but usually we just use theta. So that's the analog to displacement or position or distance or however you want to call that. So what we would have called the x back in the fall when we were doing kinematics, we're going to call theta. The units on this are radians. So there are 2 pi radians in a complete circle, or 360 degrees. You can use those translation factors as a way of doing dimensional analysis between them. So if they give you a problem and it says you've gone 4 revolutions, you can figure out how many radians that is. We generally don't leave stuff in terms of pi. In physics, we usually use 3.14 as a value for pi so that we can get a number, so that something is 53 radians or something like that, rather than some number of pi radians. It's not usually wrong, like I don't think they'd mark it wrong, but it is more challenging to plug it into your computer or to your calculator. So where we have r is the radius here. That distance that you travel, the x value, so if you're walking in a circle, for example, you're going to cover the same rotational distance, the same angular displacement, no matter how far from the center of the circle you are. That's what Calvin and Hobbes were getting at. But if you're further out, you have to go a bigger distance walking. Even though you've covered the same angle theta, you're covering a bigger distance walking. So the translation factor between distance and angular displacement is going to be the radius. So if we have r times theta, that's going to give us what x is. So angular velocity, same idea. Linear velocity is going to be v, so that's tangent to the circle. And so that's if if we were driving a car in a circle, that's what our car speedometer would say. The angular speed is omega, lowercase omega, which looks like a W. And again, that is the same no matter, the omega is the same no matter what our radius is, but the speed will be faster if we're further from the center, so the translational speed. For AP1, we define this as, speed was equal to the change in distance, or the velocity was equal to the change in displacement over the change in time. So we get omega is equal to the change in angle divided by the change in time. And for APC, we know that we can write that as a differential as well. So if v is equal to dx dt, then omega is equal to d theta dt. And the translational factor is v is equal to omega r. And that translation factor, if you look at units, that will help. This is the one that's given on your AP sheet. So v is equal to omega r. They don't give you the other translation factors between theta and x and alpha and a, but they do give you this one. So you can use that as a model. So it's not Greek is equal to Greek times r, is how I think of it. So if you were to figure out omega, that would be v over r, and that makes the units work. Radians really aren't a special unit. They're kind of a placeholder where it's really kind of nothing. So if you have meters per second equals radians per second times meters, then that gives you meters per second. So this direction stuff, you don't really need to know. So I give it to you here to be complete, but if you don't know it, it's okay. It's a right-hand rule thing. You just put your fingers in the direction that speed is. Your thumb points in the direction of the angular momentum, or angular velocity, sorry. And then, you know, that's that. But again, we don't really need to worry about that. Linear acceleration is a, let me move my face, there. So linear acceleration is a, that's what we've been talking about, that translational acceleration. Angular acceleration is alpha. So the acceleration, linear acceleration, was the change in speed over the change in time. So we can replace those translational values with the Greek values. So alpha, the angular acceleration, is equal to the change in angular velocity divided by the change in time. For APC, we know that we can make those derivatives. Positive angular acceleration is counterclockwise by convention, but honestly, it doesn't matter the way that we use it. So I tell you that to be complete, but it's not crucial that you know it. Okay, so next up, remember circular motion, long time ago? So the centripetal acceleration points towards the center of the circle along with the radius. This is known as radial acceleration also. And we had the equation AC is equal to v squared over r. And then there was this other part, the omega squared r, that I said we'd get to in January. Ta-da, here we are. We're here in January, and there it is. So in order to figure out AC, if we know the angular velocity, we can square it times r, and that gives us the centripetal acceleration. We can also translate between that tangential acceleration, which we call A, and the angular acceleration, alpha, the same way that we did with speed, the same way we did with angular displacement, and multiply by the radius. If you need total acceleration, so if they're asking you for all the acceleration and your object is moving in a circle, it's going to have tangential acceleration and also centripetal acceleration or radial acceleration. And because those will be 90 degrees to each other, you can use Pythagorean theorem. So tangential is tangent to the circle, so that's going to be perpendicular to the radius. So then you can use Pythagorean theorem to get your total acceleration, and there's a picture of that. So those two being perpendicular. And here's a summary of everything. So the conversion between translational and rotational variables. So displacement is x, and that's meters. Angular is theta, and that's radians. Velocity, translational, is v, just like we've used before. V0 is the velocity that it starts with. And then angular velocity is omega, not w, omega. And the initial angular velocity is omega 0, and that'll be radians per second. Acceleration, translational, is a, and then angular is alpha, and that's meters per second versus radians per second squared. so meters per second squared versus radians per second squared. Time doesn't change. Yay, one variable that gets to stay the same. Okay, so equations of motion, we're going to do more with this a little bit later on, but you can use, and some of these are actually on your AP sheet, two of them are, you can use the analogs in these equations. So if V equals V0 plus AT, you can rewrite that as omega equals omega 0 plus alpha t. So just taking not Greek and replacing it with Greek, so the Greek analog, and it all works. And the reason why is because if you put those in there, you're going to have omega r and omega 0 r, and you're going to have alpha r if you substitute those values in, and the r's are going to cancel from everything. So it works, and if you want to spend more time on this slide, you can. For APC, this is always true. So these same relationships hold as they did when we did this with translational motion, that if you have angular velocity, if you take the slope of that, that is the same as taking the derivative. That's going to give you the angular acceleration. And I think I'm missing some stuff in the slide. Nope. Okay. And then if you are taking the slope or derivative of the displacement, angular displacement, that gives you the angular velocity. If you take the integral of the angular acceleration dt, that gives you the angular velocity. And if you take the integral of omega t dt, that gives you the angle. Typically, the ones that we're using are going to be theta and alpha. Those are the primary ones. But the same thing with the area under the curve. That's what an integral is. So area under the curve of acceleration time is going to give you velocity, and area under the curve of velocity time is going to give you the angle. So an example, a knight swings a mace 1 meter radius in 2 complete revolutions. What's the translational displacement? So x is equal to r theta, that's that conversion factor. 2 complete revolutions is going to be 4 pi radians, so that's what your theta is. We could also show that step where 1 revolution or 2 revolutions over 1 times 4 pi radians, or 2 pi radians per revolution will give you 4 pi radians. And so x is going to be equal to 12.6 meters in this case. Another example, compact disc player designed to vary its rotational velocity. So the point being read by the laser moves at a linear velocity of 1.2 meters per second, which is really kind of cool, I think. So the CD's rotational velocity in revolutions per second. So we get to do a little bit of converting here as well. So we know that omega is equal to V over R. So we can figure out how many radians per second that is. And then in order to figure out how many revolutions per second that is, do some dimensional analysis. So it's 2 pi radians per revolution. We want to set it up so that radians cancel, and that gives us revolutions per second. Next one, this is for APC. So again, getting at that calculus relationships, so you can spend some time on that if you want to, you can pause. Here, another problem is just basic kinematics. I always find it easier when I'm doing kinematics problems to write the givens. So I don't always do that with other problems, because usually we're writing free body diagrams, or we've got diagrams that we're labeling, or maybe a table if we're doing momentum. But with kinematics, I find it really helpful to do givens where we list the variable equals and then whatever it is, because that allows me to figure out what equations are going to work. So for this problem, we know the angular velocity that it starts with is going to be 1.5 radians per second. We know the angular acceleration is 0.3 radians per second squared. And we want to know, after a time of 2.5 seconds, what the final angular velocity is, so omega. So we use the V equals V0 plus AT equation, just all Greekified. So omega equals omega 0 plus alpha t. And plug it in, and you get your answer. Then for part B, we're looking for what angle has the wheel turned. So we're not interested in degrees, we're interested in radians. So if you ever see the problem that says through what angle has the wheel turned and they don't tell you what to put it in radians. So theta is equal to theta 0 plus omega 0t plus 1/2 alpha t squared, and plug it in. So again, that's equivalent to x equals x0 plus v0t plus 1/2 at squared. So same equation, just Greek. This problem, you have a multi-speed bicycle. The rider can select the radius of the rear sprocket that's fixed to the rear axle. The front sprocket of a bicycle has 12 centimeters. We want to keep the angular speed of the front sprocket at 0.6 revolutions per second. What is the radius of the rear sprocket for which the tangential speed of a point on the rim of the rear wheel will be 5 meters per second? And then they give you the radius of that wheel. The most important part of this problem, besides remembering to convert centimeters into meters, is knowing that that wheel's tangential speed is going to stay the same. So that V is going to be the same, and that helps you solve it. So we can figure out what omega is. We can figure out V. V is constant for both sprockets. And then from there, you can figure out what the radius needs to be. So I'll let you look at that in more detail if you want to. Next problem, we've got a classic Corvette starting from rest and speeding up with constant tangential acceleration of 3 meters per second squared on a circular test track of radius 60 meters. The car is a point particle, so we don't have to worry about center of mass or anything like that. So this is just getting at those definitions of acceleration. So if we want radial acceleration, do we want angular acceleration, that kind of good stuff. So here we go. Angular acceleration, we can convert that. So we'll go on to the next slide. By taking angular acceleration as a over r, that gives us 0.05 radians per second squared. The next part, we're looking for angular velocity. So we can use omega equals omega 0 plus alpha t. Plug that in, that gives us 0.3 radians per second. And then if we want radial acceleration, same thing as centripetal acceleration, we could do v squared over r, and we could convert what omega is into v, or we can use the special new equation that we have, omega squared r, and that gives us the answer in meters per second squared. So it's all good either way. Next up, torque. Torque is the rotational analog of force. So torque is related to the amount of force that there is, but also with a lever arm. And looking at this lug nut here, you know, if you just take your fingers and you try to pry off the lug nut with your fingers, you're not going to be very successful, hopefully, you know, if it's not too loose, which is why you use a wrench. So the wrench has a longer lever arm, which makes the amount of force that you're going to use in order to turn the wrench be less. And that's one of the things that we're going to take a look at today. So the APC equation that they give us is torque is equal to R cross F. And that cross is not just multiplication, it is actually the vector cross product. In AP1, they don't tell you that, they just tell you that they have to be perpendicular to each other. So R perpendicular F, and I'll give you the rest of that equation in a couple minutes. R is the distance the force is applied from the pivot point, from the point of rotation, which we call the lever arm. So wherever it's pivoting from, where you measure from the pivot to where the force is applied. The force is the force applied perpendicular to the displacement that causes the rotation, or you have to look at the components, and I'll talk more about that in a minute. And the X means the vector product, so the cross product. So a little bit about cross product, and I'm not going to spend very long here. Again, we don't really care about the directions, so don't really worry about it. If you want to figure out the like official direction, you can, but it's not important for our problems. So you can use the right-hand rule. You have to be a little careful with this one, who you're pointing your fingers at. Your thumb is going to go in the direction of C. So C is the thing that's being cross product. A is going to be the direction of A, your index finger, and then your middle finger points in the direction of B. So everything is perpendicular to everything else. So that's how you figure it out. But again, not important for our purposes. So a little bit for APC, just what's on your AP sheet. Whoops, let me hit that one more time. So the third page of your AP sheet gives you the vector products. I love this because before they started doing this, people were always switching which one was sine and which one was cosine. It's right there on your AP sheet now, so it's awesome. If you have a dot product, which you can see I put from the first page on there, the equations that use dot product, that was work. So work was equal to F dot dr, and also power was F dot V. So that's the things there times the cosine of the angle between them. If it's cross product, we use the sine. So if we have torque is equal to R cross F, that means that you're going to have RF sine theta. And angular momentum we'll get to later, that's what L is. That's also a cross product. Okay, so getting to that. So if you're looking for torque and you want to know what it is, the torque is going to be RF sine theta. So just as I said, that cross product becomes a sine theta on the AP sheet. That's the equation that they give you is RF sine theta, and also the R perpendicular F. If you want to know direction, you can use the same right-hand rule that we used in magnetism. If you took regular physics, fingers go in the direction R goes towards F, and then your thumb is the torque. So in this case, you could also use the three-finger version where we have torque points upwards, and then what pointer finger goes in the direction of R, middle finger in the direction of F, and then that's your torque. But again, the direction is not crucial because we will be using these in problems. Again, the convention is that positive torque causes counterclockwise rotation, but we basically approach this the same way we did with free body diagrams. Make the acceleration whatever direction you want it to go in, so you can make the sum of the torques be in whatever direction you want to go in. So don't stress about the direction at all. So a couple of examples here. If we apply a force perpendicularly, which is that leftmost picture, that's an angle of 90 degrees. The sine of 90 degrees is going to be 1, so you're going to get all of that force that you apply going into torque. The upper right-hand picture, we're at an angle, so it's a little bit less torque overall. And then the bottom picture there, you're not going to have any torque at all. So if you just push on the wrench, you know, doesn't do anything. It's not going to turn anything. So because the sine of the angle is going to be 0. Okay, so at this point, I want you to pause the video and go take a field trip. Find a door. The self-closing heavy fire doors are the best. So if we were at school, this is totally what we would do. But the next best are heavy exterior doors. If you use just a light interior door, you really can't feel it very well. So, you know, use your front door or garage door or something like that. The amount of torque that's needed to open and close a door stays constant, but you're going to be changing the lever arm distance. So what I'd like you to do is really change it. So try pushing the door open and closed. You know, don't use the doorknob, just kind of push on it maybe with one finger, you know, way out at the edge so that it's a big lever arm. And then also try to move the door closed or open by pushing really close to the hinge, making a really small lever arm. So just, you know, maybe an inch or something like that. And then try changing the angle, like pushing in the middle of the door, but instead of pushing straight on at 90 degrees, try pushing at a big angle and see how that feels differently with the force. We've all probably done this where you're at a store and you push the door and you think you're pushing on the side that opens, but in fact you're pushing on the side that the hinge is on and the door doesn't really move very much and you feel really embarrassed. But next time that happens, you can think of it as being like a torque practice or something like that. So pause the video and try that. Here's an example. So here we have 125 newtons applied to a nut by a wrench. The length of the wrench is 0.3 meters. We want to know what the torque is. The angle is 90 degrees, so the sine of that angle is 1. The force, we know R. So if you multiply all of that, that'll give you the torque. Just a quick word about units on torque. We use newtons times meters because that's what we've got, force times distance. That is actually the exact same thing as a joule. So joules are also newton meters, but we never ever use joules with torque because it's just convention. Trying to separate the two of those out, torque is going to be newton meters and energy is going to be joules. So just know that. And then direction, again, we don't care about. Another example, here you're figuring out what the torque would be if we change the angles. And you can look through those examples in a little bit. Here we're solving that torque equation for R, figuring out what the radius of the lid would be if we apply 235 newtons of force and get a torque of 155 newton meters. One of the things to think about with this is that anytime you have force acting on the edge of a circle, it's going to be tangent typically, which means that you're going to have an angle of 90 degrees. This is awesome because the sine of 90 degrees is just 1. And you'll find that in many of our problems that we do, the angle just ends up being 90 degrees, which is great. Makes life easier. So the next problem here, figuring out net torque. So this is why I said direction doesn't really matter. We've got two different forces. Notice how they're all 90 degrees to the circles. So it doesn't, that 135 degrees there, totally a red herring because the radius of your circle is 90 degrees to the direction that the torque is being, the force is being applied. So it's 90. The 35 Newton force is going to tend to rotate this clockwise. The 18 Newton force is going to tend to rotate it clockwise. And the 28 Newton force is going to tend to rotate it counterclockwise. So what you do is you pick a direction to be positive. I'm going to make clockwise be positive because more of my forces are pointing in that direction. So this is just like when we did free body diagrams and you had some forces pointing up and some forces pointing down. We made one of those directions be positive, the other direction be negative. So when we did the net force, we were subtracting forces from each other. Same thing with torques. If we make the 35 Newton force torque be positive, the 18 Newton force torque be positive, and the 28 Newton force torque be negative, then we can find the net torque by combining those all together. And the next slide will show you that. So I've calculated all of those torques. Because it's a circle, everything is 90 degrees. So the first torque, that 35 Newton one, 4.2 Newton meters. The second one, 4.32 Newton meters. Both of those were clockwise. And then the counterclockwise one ends up being 6.72 Newton meters. So we take the two clockwise ones, those are positive. The counterclockwise one I made negative. And so overall, my net torque is 1.8 Newton meters clockwise. So you don't need to worry about positive and negative and what direction's what. Just you need to know what direction it's rotating in, and that's really it. That's the important part.